If you look up physics in a dictionary, you'll probably find a fancy definition with the words matter, light, space, and time. But what they're really getting at is mechanics, treating the universe like a machine. We're always trying to reduce physics down to mechanics, and I mean all physics. Hey crazies, every good mechanical analysis begins with labeling locations. Let's say I want to tell you exactly where this dot is. One option would be to find several landmarks we both know, draw lines to them, and measure the lengths of each line. We've actually done this for Earth as part of a message to aliens. This is geometry, and after basic arithmetic, it's probably the oldest form of math. It's the branch that deals with relationships between points, lines, surfaces, and solids, which is pretty much how humans see the world. But geometry by itself has limitations. Mechanics only exists because we found a way to connect geometry to other forms of math, which only arrived like 400 years ago. That's when this guy showed up, René Descartes. What he did was introduce the concept of a coordinate system to mathematics. Rather than our dot being measured from a bunch of landmarks, it would simply receive a short set of numbers along an agreed upon set of axes. Of course, this wasn't a new idea. Maps and globes had coordinates for millennia before Descartes ever started using them. But his diagrams are the earliest record we have of someone using them in abstract math. You're probably most familiar with the coordinate plane. That's the one with an x and y axis at 90 degrees. We named it after René Descartes, but it never actually appeared in his publication. His version only included a single axis, and one so vague you almost won't even notice it's there. The modern coordinate plane was developed by other mathematicians later on and just named in his honor. The concept of a coordinate revolutionized math and ultimately physics. Take this road, for example. We could decide this spot is 0. From there, each other location along the road will receive a non-zero number, a coordinate, if you will. A system of these coordinates is the canvas upon which we define everything else about a physical scenario. A long road only happens to need one axis, but other situations may call for 2 or even 3. Space is three-dimensional after all. The 3D version looks something like this. 3 axes, all at 90 degrees to each other. #Z up for life! Then again, you're not limited to these Cartesian types. Maybe it would be more useful for you to label distance from a center point and an angle around a circle. Or maybe you need a system that's more specialized or exotic. You should choose the one that's going to work best for you. These are all just mathematical tools. That being said, mechanics requires more than a coordinate system. I mean, it's good enough for a sign or a bridge or something. But the interesting stuff happens when objects move around. And motion requires one more thing, a clock. Once you have a coordinate system and a clock, now you're doing mechanics. That's the study of the motion of physical objects. We're talking velocity, acceleration, forces, physics. Say we have a car traveling at a steady 40 miles per hour, and we want to know how far it'll go in 15 minutes. Well, 15 minutes is a quarter of an hour, so the answer is 10 miles. That's just a little unit analysis, or what we sometimes call dimensional analysis. And that name, dimensional analysis, it gives us a hint about where we're going with this. The typical x and y are dimensions, but they're also abstract placeholders. Nothing says either of them has to be location related. So let's get a little loosey-goosey with our axes for a minute. Say we make the coordinates speed and time. The car will draw a rectangle, and the area of that rectangle is the distance it travels. A longer time means a longer rectangle, which means more area, which means more distance. We just changed this question from algebra into geometry. And the specifics don't even matter. If the car is going faster, that's a taller rectangle, which means it covers the same area in less time. This works even if the speed changes. That's what makes coordinates so useful in physics. They link geometry to algebra so we can use both. You can make any well-defined measurement a dimension, and therefore an axis on a graph. Force against time might be useful during collisions. Position against velocity is good for repeated motion. And we're always trying to reduce every type of physics to mechanics because it's what we understand the best. Thermodynamics? That's just the mechanics of molecules. Quantum mechanics? We're not going to talk about that, but it is mechanics. Now, this might give you the impression we're peering into the machinery of the universe. I mean, it's right there in the name. But if you look closely, that perspective doesn't really hold up. Even in the original car example, there's some flexibility. We could have just as easily chosen this spot as 0, or that spot. We could have even chosen the opposite direction to be positive. The road and the car do not care. All the physics we do happens on a kind of transparency layer we place on top of reality. We're not peering underneath a veil, we're imposing our own perspective. The universe has no up or down, it has no coordinates, it doesn't keep track of velocity or force. The universe just works. So where does physics end and reality begin? Let me know what you think down in the comments, and until next time, remember, it's okay to be a little crazy. Let's get a little.
The smile in your mouth is like, absolutely not.
Right. Today's gonna kill me. What is with the noises today? It's never this loud. Oh, okay. It's not. It wasn't even this loud the last several times I filmed here. Yes.